Cool Planet's decarbonization software Clarity can integrate with your systems and utilities, enabling you to measure, manage, and reduce your company's emissions with ease using a single platform.
Welcome to our masterclass series. Our masterclass this afternoon is a deep dive into heat pumps. It's a really big topic at the moment, and there's been a lot of interest in this masterclass. Great to see so many of you signed up. Our panelists this afternoon are Global Director of Refrigeration, Mr. Dave Goldberg, and he's in conversation with Alan Keogh, our CEO here at Cool Planet. There's a lot of information to be imparted this afternoon, and I'm going to hand over to you now, gentlemen.
Thanks, Sinead. Dave, welcome.
So you're the expert as well, then?
Well, I wouldn't say that at all.
Well, it is heat, isn't it? So
Sinead is overly generous. So I'm here just to ask the questions, really, I suppose. So as Sinead said, obviously a lot of heat pump talk these days, you know, in the whole net zero thing and decarbonization. Obviously, there's a lot of focus on heat pumps for kind of residential solutions, and you know, I think the UK in particular is talking about installing 500,000 to 500,000 heat pumps a year up to 2030 to try and hit the overall decarbonization goals, carbon reduction goals. But today, I suppose what we're going to focus on is industrial heat pumps and, you know, how heat pumps may be a solution for reducing carbon emissions from industrial plants, etc. So it's hopefully going to be an interesting discussion for everybody. So Dave, maybe just start with just a quick background. You've been in this business for what?
40 years.
82 years
82 years, yeah. 40 years, believe it or not, in refrigeration. In my apprenticeship with Frigoscandia, and worked in industrial refrigeration all my life, really. Always been interested in energy efficiency since early 2000s, when it wasn't really a thing. So yeah,
and is it
around the block?
Is it a thing these days, do you think, in industrial refrigeration? I mean, you think the people in the industrial refrigeration business are focused on energy efficiency?
No, is the answer. They say that they are, but they're just ticking the boxes, really. The plants that we go to, you can tell there's no emphasis on energy efficiency. You've always got a disjoint between fridge contractor and customer. Customer wants a temperature, fridge contractor just wants to give them that temperature, so they never see electric bill. So as a general rule, I think they're trying, but I don't think they're trying hard enough, which is great for us because it gives us a business.
Yeah, okay. Maybe give me a couple of examples of how does that manifest? How does that lack of efficiency and lack of focus on efficiency, how would that manifest in a typical meat plant, for example?
Well, your customer gets a problem with temperatures, your fridge contractor gets called out, he has a look at the problem, all his job is to get the temperatures down. So there's various things you can do on a fridge plant. You can frig things to get temperatures down, you can lower suction pressures. There's all sorts of games you can play, but obviously the impact is on energy. So the guy that gets called out at midnight, messes around with the plant, gets the temp down, goes home, never sees electric bill. So then the next guy comes from the same company, he doesn't know what the set points are, he just says, yeah, temperatures are okay, fridge plant's running, plenty of refrigerant in it, jobs are good, and he just gets left. So nobody actually sits back and says, well, why is that running as it's running? Surely it could run a lot more efficient than that. Yeah.
So that kind of sounds like a couple of problems or issues wrapped up into one. One is maybe a training issue or a focus issue for whoever's, you know, tasked to go off and wind down the plant. But maybe there's a bigger issue, or as big an issue. Customers don't see that change, they don't see that impact until maybe a couple of months later they're kind of seeing it on their bills trending up. Is that the case? That the visibility of...
Yeah, but then also because the customer production is changing all the time and the weather's changing all the time, so the customer don't really relate to. The customer's not a fridge engineer, so the customer doesn't walk around generally and say, well, why is that fridge running like that? Or why is the 3 compressors running today? There were 2 running yesterday. They just think it's production. So it gets masked in many things, production, weather, and then the fridge guys are just there to make sure they get the temperatures. That's the bottom line. And if you're a fridge contractor, that's what you pay to do. You know, you pay to fix the fridge plant, get it running, and make sure the customer can get product out of it. And that's the focus. Let's get the products out the door.
Yeah. And you see signs that things are changing in that regard?
No. The honest answer is no. No, I don't. No.
Okay. Even with energy prices 3x what they were, and net zero targets, and
well, my phone's not ringing a lot to say come and sort my fridge plant out. The energy prices are going through the roof. People just seem to be accepting it from what I can see. I think the big corporates are saying, look, we need to do something about this, decarbonize, which you know more about than I know more about. And they're saying, look, let's have a look at this. So the bigger companies are setting targets, but it makes me mad when you watch the TV and everybody's talking about there's not going to be enough energy, and that there's that many industrial facilities out there that's just burning energy that don't need to. In a food factory, your fridge plant's going to be 50% of your electric bill. In reality, it could be. I think the best project we've done is 55% savings in one brewery. So, that's 25% of a 25% that site's electric bill. Just be wasted, all the products still going out the door.
Yeah. Yeah. So maybe moving on to kind of maybe the topic du jour, heat pumps. As we kind of mentioned, there's a lot of talk about heat pumps. In fact, I see, there's kind of a lot of indicators of that. Two recent ones I saw was Biden in the US as part of the kind of IRA, which is an unfortunate kind of acronym, but the Inflation Reduction Act that passed there a couple of months ago. As part of that, they've actually included heat pumps as part of the Defense Production Act, which goes way back to World War II, where they kind of requisitioned kind of production for in the US industrial economy for kind of war efforts. So kind of an extreme move to focus production on heat pumps. So it's quite interesting that it's kind of getting out there. The other kind of indicator is GEA, big refrigeration production contractor. They build a lot of refrigeration equipment. They've rebranded their refrigeration arm GEA cooling and heating to emphasize the focus on heating as well as cooling. So I mean, just a basic question to kind of start the discussion on heat pumps. What is a heat pump, Dave?
Well, effectively a heat pump is a refrigeration compressor. That's basically it. It's just running at different pressures, and historically a refrigeration compressor would emit its heat into the atmosphere, whereas a heat pump's capturing that heat. So it is just a fridge compressor. People say, oh, this fandangled super heat pump. It's not, it's just a fridge system. It just operates at different pressures. And instead of emitting the heat, you capture the heat in various ways. So if it was an AC system, a split system, you'd heat an office block with it instead of putting it into atmosphere. So it's not this super fandangled thing that everybody makes out it is.
Well, the other thing you hear a lot is it's a refrigeration plant that runs in reverse. What's your view on that?
Not really, no. It's a refrigeration plant. So if you had an air source heat pump, it would use the air as the source to prime the heat pump, and then so you would use the condenser that's outside that rejects the heat. That becomes the heat absorber. So in some ways, you are reversing the refrigeration system, but on industrial applications, no, not really. You're just capturing the heat and making it more efficient.
Doing something useful with heat.
Exactly, instead of putting it, outside to atmosphere. That's what you're trying to do.
So there's a lot of talk about priming the heat pump, and priming a pump is a maybe a useful or not a useful analogy, but what does that mean, priming the heat pump?
So if you imagine a fridge plant, if it's cooling a chill store or a cold store, it's removing the heat from the infiltration of the product. So that's the prime for the refrigeration system. So exactly the same applies to a heat pump. So you need the prime to make the refrigeration compressor work. So you need to give it heat from somewhere. So I suppose if you use an analogy of a fridge in your house, so if you put an electric meter on your fridge and there's nothing in your fridge and it's down a temperature, it doesn't use any energy. Open the fridge door, put 48 cans of beer in at 20 degrees, shut the door, there's a heat source, look at the energy meter, and the fridge is going to run and run and run to remove the heat. So the prime is just a heat source, and it depends where you get it from. of what the quality of the prime is.
So to use that useful analogy, so 48 cans of beer, 2 trays of beer,
Yeah.
a typical night in. So you put it in, you take it out of Lidl or Aldi, you put it in the fridge at ambient, whatever it is, 18 degrees. And obviously you want the fridge to cool that down to 4 degrees or 5 degrees, something like that. So all that energy that's been sucked out of the cans of beer is the prime, and then the heat rejection presumably then is all the heat that you feel behind the fridge at home.
Exactly.
Which has been,
yeah. So if you looked at the energy meter, you're obviously using electricity. So and all you're doing is taking the heat out of the beer with the refrigeration system, and all the heat's then going into your kitchen.
Yeah.
So atmosphere. Whereas a heat pump, instead of that going into the kitchen or to the atmosphere, you would put that into some sort of secondary cooling medium, whether it be water, glycol, or whatever.
To do something useful in a factory.
Yeah.
Okay.
So instead of wasting it, use it.
Okay. So if you take that concept of the prime, what does a prime, where do you get that heat from in a typical factory, that you're recovering some heat to pump it and then do something useful with it? Where do you get that heat from?
Well, there's a majority. There's lots and lots of places you can take the heat from. So this is the question with heat pumps: is that's the main consideration is the application and where do you get the prime from? So you can get the prime, say, from, if there's a glycol or chilled water system, you could take the prime from there. You could take the prime from the ammonia plant, from the discharge gases, as long as you put regulators in and you make sure the prime was where it needs to go. So there's lots of various places. You could even take it from the air source. So you could even put coolers in there and use a heat pump to chill the space. And instead of rejecting the heat to atmosphere, you put it into water.
Okay. So that makes sense. So that's the sucking side. So we're sucking the heat. And what's a good prime versus a bad prime, and why is it good versus a bad prime?
That all depends on what temperature you want out of the heat pump. So if you're heating water, is effectively the best prime is the highest prime, because if you wanted to generate water at 65 degrees, if you could put a prime into a heat pump at 30 degrees, the heat pump's only lifting 35 degrees. So the efficiency of the system is how much the compressor lifts. So if the compressor only has to lift 35 degrees, then that becomes a lot more efficient than if it's lifting from 0 to 65 degrees. Okay. So the higher the prime, the better it is.
Okay, so let me see if I get this straight. So to maximize the efficiency of the heat pump, which presumably means minimize the amount of electricity you put into it, which then reduces your cost, you want to minimize the temperature lift from the cold side to the hot side.
Basically, yeah. So any refrigeration compressor, the efficiency is based on the lift. So if the lift is quite wide, then the efficiency is going to be lower. So the COP, so coefficient of performance. So every kilowatt of power you put in is how many kilowatts, in this case, heating you get out of it. So if you lift in from 0 to 60 degrees, you're probably going to get a COP of 3.5 to 4. If you lift in from 30 to 65, you're going to be at 8. So you're reducing the lift. It's the same with the refrigeration system. To make the system efficient, you need to reduce the lift. Exactly the same thing applies to a heat pump.
Okay, so if you go from a COP of 4 to COP of 8, you've effectively halved the amount of electricity you need to run the compressor.
Exactly, for the same capacity. Yeah.
For the same heating capacity. Yeah. Okay. So obviously it's critical then to figure out where you get a good temperature prime from. So then presumably if you're using air source, so obviously in residential, most most heat pumps will be air source, and obviously in the winter the air could be -5 in UK and Ireland, colder in continental Europe obviously. So then if you're in a factory, for example, with an air source heat pump and you want to generate, say, 65-degree water, say, for example, a meat processing factory where they need 65-degree water for washdown, that's a reasonably high
It's a lift, big lift.
lift across the compressor. So your efficiency is going to drop, especially in the wintertime when you have -5 air versus maybe 20-degree air outside in the winter. In the summer.
Exactly. So if you thought about air source heat pumps, they're not great for Northern Europe, but if you haven't got any other heat source, then what else can you do? It's still going to be more efficient than using an electric boiler. But air source, if you're in Dubai, air source is absolutely brilliant because it doesn't drop below 20 degrees much. So again, it's down to the application.
Okay.
I can't stress that enough. When you're doing a heat pump, you need to get to the application. You need to understand where's the heat coming from, where do you want to generate the heat, and how much heat you actually need. And is it going to be a constant flow? Is it intermittent? There's a lot of factors. You can't just stick an heat pump in and say, there you go, I'll tick that box. It doesn't work that way.
Yeah. Okay. It seems it doesn't.
No, it doesn't. It doesn't.
Yeah.
Well, people will say, sell me a heat pump. Well, what do you want a heat pump for? Well, I just want a heat pump. Well, no, that's not the right answer.
Yeah.
How
are you going to
plug? Where's the prime? What temperature?
And where are you going to re-inject the heat, and how can you minimize that?
Yeah.
So in terms of primes, then top of the head, possible heat sources for primes that occur to me are, any kind of waste heat. And, as we know, I mean, there's a statistic that says 70% of primary energy in the world is wasted. And a lot of that waste is in the form of waste heat. So you can see it everywhere in factories, big air handlers that exhaust out, 25-degree air into the atmosphere because they suck it out of a pharmaceutical plant.
Cooling towers.
Cooling towers.
Booms of steam going up in the atmosphere, that's all heat, so that could be a prime.
Yeah.
So any waste source of heat, don't matter where it's from, it could be from the refrigeration system. If it's got a cooling tower, you can use the water from the cooling tower. If it's going to an evaporative condenser, you can take the discharge gas. If there's waste heat from effluent, if they're dumping hot water down the drain, take the heat from the hot water. So it's the highest source of prime is what you're looking for.
Yeah. Okay. All right. Interesting. So then on the other side of the heat pump, so you want to again, to maximize that COP or coefficient of performance, you want to minimize the temperature that you're generating the heat at. And obviously in a factory that can be challenging, but they have set temperature requirements. Washdown water needs to be at 65 degrees for sterilization purposes. Low pressure hot water into an air handler in a pharmaceutical plant in the wintertime probably needs to be 70-75 degrees just to get 20-degree air going into the clean rooms in the pharmaceutical plants. I suppose an interesting analogy to think about is if you look at again using the residential kind of example, if you've got an air source heat pump, ideally you want the heat coming off the heat pump to go into maybe underfloor heating, where you can use a lower temperature water than radiators on your existing size radiators, because the boiler in your house generates water at 80 degrees. They're smaller radiators to heat up the room to 22 degrees. But with a heat pump in your house, you're going to struggle to do that, aren't you?
Well, the ironic thing is that if you put an energy meter on a heat pump in summertime, it will be a lot more efficient than it would in wintertime. But obviously in the summertime, you don't need your domestic heating. So this is the problem with air source heat pumps. When you need them the most, become the less efficient. So if you're looking at like +5 to -5, it's normally high humidity. That's worse for a heat pump because it's harder to get the heat out of the atmosphere, and it can cause it to ice up and it has to defrost. So air source is okay, it's better than not having it, but it's not an ideal thing, not in Northern Europe anyway.
Yeah. Okay. So in a factory then, where have you kind of looked at reusing the heat that comes off the heat pump, and what kind of temperatures are you looking at?
Well, there's various temperatures. I mean, you don't have to generate the heat pump heat because it depends again on the source. So if you haven't got a very good source, even if you're generating water to 50 degrees and topping it off with a boiler, it's better than not generating it all and sticking the heat to the atmosphere. But you can generate up to 90 degrees on a heat pump. I mean, that's getting up to the limit of an ammonia heat pump. We have looked at schemes using butane where you can actually get up to 120 degrees, so you can effectively generate steam. So there's a massive range of what temperatures you want to generate, and again, it depends on the application, really.
And is there much value in, like, I think my kind of view on decarbonization generally is that we are all in our houses, but also, people in factories and plants, etc., are going to have to get more involved in, flexibility and running the plants more dynamically. One example I think we've discussed before is, if you've got a low pressure hot water circuit in a pharmaceutical plant, probably because of the size of the coils and the air handler, in wintertime, there's 0 degrees or 5 degrees outside, you're probably going to have to use, unless you change all the coils, which is possible, but it's a bigger job, 80-degree hot water in the wintertime. But that hot water presumably could be reduced in temperature in summertime, or 9 months of the year probably, which will allow you to run the heat pump more efficiently to generate that hot water.
Yeah. So the higher the temperature, the less efficient it becomes. And obviously there's a certain stretch on heat pumps, depending again on the prime, is how hot you can take the water. So something's better than nothing, in my opinion. If you've got a chiller out there and you've got in a pharmaceutical, you're dehumidifying and you've got hot water, why would you dump the heat to atmosphere? Recover the heat. It's better than going into a boiler at 10 degrees when you can stick it in at 40 degrees.
Agreed. And I heard you mention a couple of minutes ago just ammonia, and there's a lot of different gases out there. Again, back to the point, a heat pump is a refrigeration plant. There's different refrigerants available. What's kind of the most common, and what's the best, I suppose?
Ammonia, by far. It's a natural refrigerant, 0 GWP. If you're going to tick the box and you want to reduce your carbon, why would you put an HFC heat pump in that's not as efficient and it's still got global warming potentially? It doesn't make sense to me. Ammonia for me is always the way, and it's a good heat source, ammonia.
And what's the improvement in efficiency in ammonia for the same kind of duty?
You probably 15-20%, depending on the HFC refrigerant, but as a general rule, 15-20%.
Okay.
I mean,
when people hear, okay,
the equipment, it's different equipment completely.
And when people hear ammonia, they maybe alarm bells start to ring. What's your view on ammonia from a kind of health and safety perspective versus F-gas?
Well, the newer systems are very, very low charge. So you're only talking for 500 kilowatt heat pump, you'd be looking at 20 kilos of ammonia. So it's a factory built unit, it's all self-contained, you've got detection systems, you can buy it fully enclosed with ventilation systems. I don't really see an health and safety issue with it at all because the volume is so low.
The volume so that when you say the charge, that's the actual just
the amount of refrigerant that's in there.
Massive refrigerant. Yeah. Okay.
If you'd imagine 10 years ago, for a 500 kilowatt heat pump, you'd have had 500 kilos of ammonia.
Yeah.
Now you're down to 20.
Brilliant. Just to jump in there for 1 sec, gents, just to let everybody know that if you have any questions this afternoon, please pop them in an email to me. You all have my email address from the invite this afternoon, and it's sinead.halligan@coolplanet.io. I will pass questions on to Dave and get back to you as soon as possible. And now hand it back to you, gentlemen.
So ammonia, so 20 kg charge, which is quite low, but presumably there's safeties in place as well, detection, etc.
Yeah, depending who you buy the heat pumps from, you can buy them in an enclosure with a ventilation system, the detection system, and 20 kilo of ammonia is going to dissipate pretty quick, to be honest. And you can also set the alarms to a very low level. So even if, even the HSE in the UK say you can work in ammonia up to 25 parts per million for 8 hours or 6 hours. So I'm not sure, but it's quite a bit of time. But I've worked in ammonia all my life, and I couldn't work in 25 parts per million for that amount of time.
Okay. And typically, what do they look like in an ammonia heat pump? Is it sitting outside or in an existing plant room, or
You can go
on a
anywhere.
roof, or?
Yeah, you can put it outside, put it on a roof, put it in an existing ammonia plant room. If you've got an existing ammonia plant room, it makes sense to put it in there because you've already got the detection system and the ventilation system anyway.
Okay,
So,
all right.
Okay. Well, there's no restriction where you can put it. Obviously, a roof is going to be a heavy lump of kit, so you need to make sure that the roof can take the weight.
Okay, all right. So, so you mentioned a couple of temperatures earlier. Ammonia at 90 degrees, I think.
Yeah.
So, what kind of happens with the efficiencies at those kind of levels?
Well, it's back to COPs. The higher you go, the lower the COP. So, if you're going to go to 90 degrees, you might want to think about doing two-stage. So, you take an initial prime, and then you dump the heat from the first heat pump into the second heat pump. And really, you've got to do that because of the lift of the heat pump. They can only pump a certain differential. So if the differential's a lot, if it's too wide, it's not going to be able to pump it in one go. It's too much for one machine. So you'd go on a two-stage system. So you might, for the first stage, you might cool glycol. And then once you've cooled the glycol, you'll dump the heat from the glycol from the factory. So the glycol's cooling the chill stores. You dump the heat from the first compressor into the second stage directly through a desuperator or an evaporator, and then that primes the second stage, which takes it to 90 degrees. But obviously the efficiencies can drop off.
Okay, and on the efficiencies, I mean, there's a technical efficiency, but also there's a commercial efficiency, which can be varied depending presumably on the electricity price. So presumably, if you run a heat pump at a certain lift across it, you get a certain COP or efficiency, and that doesn't change unless you change the output temperature or the prime temperature. But you can make more or less savings depending on the electricity price, presumably.
You can. I mean, I don't know. Question for you is, how's the electricity prices and all the utilities have changed? My old rule of thumb was, if the gas is 3 times more expensive than electricity, or sorry, 3 times less expensive than electricity, then the heat pump would be a viable option. So I suppose it's a question to you: what's happening now? All the energy prices are changing.
Yeah, it's a good question. We're living in a very volatile energy world, as most people know. But on electricity markets, certainly in Europe, what tends to happen in electricity markets at the moment is they're very variable. And when wind and solar are low, when the sun doesn't shine and the wind doesn't blow, prices tend to be very high because they're set by gas typically, yeah. And we all know the price of gas is gone crazy over the last 9 months or so. So when the wind doesn't blow, the electricity price tends to be high, very high at the moment. And when the wind blows in Ireland and UK, the electricity price collapses very, very rapidly. So you can get, swings of, maybe from 7 cents at the lowest up to maybe 35, 40, 50, 60 cents, in the case in Ireland or pence in the UK. So you get massive swings in the price of electricity, which is the raw material, is what you're feeding into the heat pump. So so it is definitely an area to look at, is can you either turn off the heat pump when electricity prices are very high for periods of time, or when electricity prices are very low, can you actually increase the temperature? And this is a technical question for you. Can you increase the temperature coming out of the heat pump, maybe to displace more gas? Because gas tends to be more fixed price. You buy gas for a month and it's the same price, whereas electricity varies hour by hour.
Well, it would make sense to do that. If you've got sight of live electricity prices, then obviously if the electricity is going up, then you don't want to run the heat pump. You can vary the output of the heat pump quite easily, but it depends on the heat pump that you select to start with. So there's various size heat pumps or various pressures. So one heat pump might get you to 65, another heat pump might get you to 90. The efficiency is exactly the same. So if you wanted to vary the output, you'd say, well, I'll take the higher pressure machine that gives me the flexibility to go to 90 if I want to go to 90. Again, it depends on the prime. Well, yeah, it would make perfect sense to either start them or stop them or run them hard in low electricity prices.
Yeah, okay.
But then
and obviously,
create a volume then of storage.
You need a volume for storage, which is it's an interesting point. Storage. So obviously there's lots of different types of heating loads, thermal loads in factories. There's very stable loads, or general quite stable loads, like in a pharmaceutical plant where you've got, most of the heating energy is required for space heating, cooling, heating, clean rooms. But other factories presumably have a lot more variability, more batch type processes.
Yeah,
process
heat pumps
loads.
don't like that. Heat
They don't
pumps
like
want
that.
a steady loading. If you imagine, again, it's back to the early conversation. The heat pump's a fridge compressor. So a fridge compressor, to make a refrigeration system efficient, is what we also do, is you need to make that stable. So you don't want to see spikes in refrigeration systems. So you make the plant stable. The heat pump is exactly the same. It's just another fridge plant. So don't keep sending loads to it and then stop it. Stopping starting a heat pump is you lose all your efficiency. You need a steady run. So if you want to heat 100 meters cubed of water, you need to make sure you've got the prime to make that 100 meters cubed of water, and don't stop. That's the worst thing you can do.
And on the output, if it's very variable on the output, you just say it's not a heat pump application, or how can you deal with that?
If the output's variable, you'd have to put storage in. You could put storage in for a prime. You could put storage in for heat that you generate, for hot water that you generated. So you've just got to balance the flows out. You've got to make it a very, very steady state. If you're in a facility where you're getting a prime and then it stops, and you get a prime and it stops, that's not a very good application for a heat pump. You need to run it. So if you get a prime for 4 hours and you get nothing for 4 hours, then build a storage facility that's got 8 hours of storage and well insulated. Then once you get enough prime, then run the heat pump.
Okay, all right. So tanks, basically, the storage are just presumably insulated
just
tanks.
Insulated tanks. It's nothing fancy. Just something that's going to hold the heat, whether it's from the source or from your prime, or the heat that you're generating, i.e. hot water. So it's quite common to have a tank, say, in a food facility that's 100 meters cubed. You're filling it all day, empty in the morning, it's full at night, and it's 65 degrees.
Yeah, okay. So heat pumps you're talking to a lot of customers about heat pumps. How much more than, say, 2 years ago?
Everybody's talking about heat pumps. Everybody wants a heat pump. They don't know why they want a heat pump. It's crazy. We had a guy in Australia that says, sell me a heat pump. What do you want a heat pump for? I just want a heat pump. No. What do you want a heat pump for? Don't tick the box. Get the right application. So everybody's talking about it at the moment. So, I mean, you tell me, you're more in front line than I am. Why are people suddenly turning to heat pumps?
Yeah, well, I suppose, like a lot of things, sometimes it's like, my boss went to a conference and he heard heat pumps were great, and we need to look at heat pumps. So there's a bit of that, but they are a solution for 50% carbon reduction in 2030, which is generally, or 55%, which is what the EU is aiming for. Not sure about Britain. Obviously, you guys aren't in the EU anymore. Maybe back soon. So 55%. I suppose the grid is greening. Grids generally in Europe are greening. I mean, in Ireland, we're at roughly 35-40% of the overall electricity on the grid. This year will be green electricity. Mostly wind, some solar, some hydro, obviously. And we have to get to 90% of the grid being green by 2030 to kind of hit our targets. But the electrical demand is going to increase significantly as well, as we all charge our cars and, install heat pump in our homes and houses, factories, etc. So, but the green grid is kind of a skeleton key for decarbonization of lots of other sectors, including industrial heat and home heating. So the idea is that if you have a heat pump which displaces gas consumption, which is carbon emissions, when you combust gas, it creates CO2 and water vapor. So if you eliminate the gas consumption, you eliminate what's called Scope 1 carbon emissions on your site. So Scope 1 emissions are emissions directly related to your site combustion of gas and some other things as well. Scope 2 is carbon emissions related to power generation, so the power plant down the road, and scope 3 is your supply chain.
So it's more about decarbonisation then, because the difference, I don't know, you tell me, but the difference in the prices are very similar to what they've been for the last 10 years between, you know, how much is gas, how much is electricity. And heat pumps have been out. We installed our first one 8 years ago.
Yeah, exactly. So it's back to that point again about, you know, gas pretty much sets the price of electricity in Europe generally. So while the electricity price is going up, the gas price is going up as well, and they're both going up more or less in a similar ratio. So actually, the economics of a heat pump are actually in some cases better now than they were, even though electricity is a much higher price. You know, the competing gas price that you're competing against is also a much higher price. So as long as they go up in that band, they go up and down together, you know, and that link isn't broken, and that link won't be broken for 5 or 10 years probably. You know, the economics are there. In fact, the economics are better these days, and especially when you load in carbon savings. So if you are a site that, you know, is on the EU ETS, which is the European Carbon Trading Scheme, you can then claim those carbon credits for not emitting carbon when you burn gas. Because you got a heat pump, you're not burning gas. Yeah, exactly.
And how old is that then? Because obviously it's getting a lot more popular these days. Everybody wants a heat pump. They don't know why they want a heat pump, but everybody wants a heat pump. So how long has that scheme been going?
Well, the scheme's been going 10, 12 years longer, and it's been, for most of the time, it's been a bit of a failure. Carbon was bumping along the floor of kind of €4 a ton, €5 a ton. Carbon's now, you know, 70 plus euros a ton, and it looks like it's going to stay there. And the EU will engineer the carbon trading scheme so that it will stay 70 to 100 to 110 euros a ton, because it's the jewel in the crown mechanism for achieving 55% carbon savings by 2030. Without the carbon trading scheme, that it's not possible to do that.
So similar idea to RHI in UK that never really took off. You know, that was the idea, is a renewable heat incentive.
Yeah, similar, except it's more of a market mechanism. The RHI was a tariff. You know, you produced renewable heat and you got paid whatever it was. Whereas the carbon market is a market. So, you know, theoretically, if Europe goes into recession next year or this year, you know, demand goes down, power consumption goes down, etc., the price of carbon credits could potentially fall. But the EU have a lot of different mechanisms that they can adjust how many credits are in the system, and they can withdraw credits and they can keep the price high. So it's quite a political market, obviously, and the EU have, you know, accentuated or accelerated, you know, their targets for decarbonisation because of the Ukraine situation and decoupling from Russian gas. So it's something that's going to be around for well, at least the next 10 or 15 years, I would say.
I mean, you know, back to the heat pumps, you know, we've talked about a lot of things. You know, you talk about F-gas heat pumps against ammonia heat pumps, you know, and yeah, the ammonia heat pumps cost a lot more money, but they're a different animal. You know, I suppose if you look to like everybody likes looking at car analogies, you know, if you buy, and this is no disrespect to HFC manufacturers, if you buy a HFC heat pump, it's like buying a Lada. If you buy an ammonia heat pump, it's like buying a Mercedes. So you don't see many Ladas as taxis, do you? But you see lots of Mercedes as taxis, and they're there for a very long time. So there's a big difference between the price point, you know, from an HFC, and there's a difference, as we spoke earlier, about efficiency. So if you bought an ammonia heat pump, you know, I've worked on, because I'm old, I've worked on ammonia plants that are 70-year-old, you know, fridge plants, and they're still operating. So it's just more of a serviceable item, an ammonia heat pump, and it's a lot more efficient, and it's green, you know, 0 GWP. It's what everybody should be looking at, really.
Yeah.
And again, you know, I can't stress enough is the application that you need to think about, really seriously think about before you can buy a heat pump. You need to understand, where's the heat source from, how much heat do you want to generate, what the temperature is, can I store it, do I need to buy storage? That's probably the most important bit.
Yeah, okay. And to that point about the capex of the ammonia versus the HFC, but actually in reality, the heat pump is a reasonably small proportion of the overall project. It's to your point, it's the application and the integration. So, you know, if you have the right application and integration on the prime side and on the heat reinjection side, whether it's a HFC plant or an ammonia plant, all the other pipework and the tanks and the electrical
Big
connection.
infrastructure. Yeah.
It's all the same.
Yeah. And it can, well, sometimes it can be very easy to install, depending where your prime is and where you want to dump the heat. You've already got the tanks, but for the difference that you pay from an HFC plant to an ammonia plant for the whole life cycle cost, it's a no-brainer. You cover ammonia every day a week. You won't even consider an HFC.
Yeah. Okay. And presumably, look, lots of factories have ammonia anyway, so it's not that common. They have ammonia refrigeration plants, etc.
Yeah. And you can take the prime directly off the ammonia plant. You could even, as you know, we've got a job over in States at the moment where we've actually integrated a heat pump into the refrigeration system as it is. So he's doing the refrigeration and generating the heat at the same time with primary refrigerant. Whereas most of the time people use a secondary, whether it be glycol or chilled water. So again, it's down to the design and application. There's lots and lots and lots of different tunes you can play. It doesn't have to be one set thing. You just need to really think about it and think, how is this going to fit into this infrastructure? And how's it going to be efficient? And how's it going to deliver where I want it to deliver and be available when I want it to be available?
Yeah. Okay. So it's been a great discussion, Dave. Appreciate it.
Problem.
What would you say are the 3 takeaways to anybody?
Don't buy cheap.
Okay.
Really, really, really spend as much time as you possibly can understanding why you want the heat pump and where it's going to be plumbed into and where you're going to get your prime from. And then don't over-generate the hot water. If you need water at 65 degrees, generate it at 65. Don't generate it at 75 just because 10% of the heat source wants 75. Take the mass and take the lowest temperature and get the efficiency as best as you can. And that's kind of design and application.
Or negotiate with your internal 75-degree consumer, because as we know, a lot of the time you hear in plants, it's just always been that set point. Now obviously a lot of the time for CIPs and hygiene reasons you need those temperatures, but a lot of the time as well, when we challenge the customer to say, well, why is that at 75? Maybe it could be at a lower temperature. The response is, well, it's always been that way. We feel comfortable.
Yeah, and it's down again to refrigeration systems. Is whenever they get commissioned, they get the first electric bill for that month and they think that's normal. Well, it doesn't have to be that way. Just question it every time. Yeah.
Okay, look, thanks, Dave. Appreciate it. And we'll, I don't know what else to say. You can cut that out.
Vera Lynn would say.
Guys, that was great. Even I understood what you were talking about there. And thank you very much, everybody, for joining us. I hope you got as much out of it as I did. I hope you enjoyed it as much. Any questions that you have, you all have my email address, sinead.halligan@coolplanet.io. Drop them in. I will send them on to Dave. And anybody wants to chat with him, we can set that up. Gentlemen, thank you very much for your time. Really, really appreciate it.
You're welcome.
Our on-site generation and storage solutions can decarbonize your energy and benefit your bottom line. We look after everything from green energy brokering and battery storage to demand response and solar arrays.